Thank you so much. I'd also like to thank the organizers. Happy to be here. My name is Mike, and I'll be talking about this work, which is joint with collaborators Nikolai Toms, who's also in the Q&A, as well as with Jonas Peters, both of them from the University of Copenhagen, and also with my advisor, David Sontag. And we'll be talking about regularizing towards causal invariance using linear models with proxies. So our motivation here is not so much causal effect estimation as it is robustness to dataset shift using causal principles. So for instance, in a healthcare context, you might imagine we have some disease that we're trying to diagnose or predict. We have some features that may be causal of that outcome, and we may have some other features that are caused by it, like symptoms. And this makes up our observed distribution. But in most real-world prediction problems, as well as in many causal inference problems, perhaps, there are a variety of unobserved factors that matter but are not observed directly. So in healthcare, for instance, socioeconomic factors, social determinants of health are all very relevant. And you can think of that concretely here as things like income and distance to nearest clinic, which may influence access to healthcare. And we may be concerned with a scenario where we are training a model in one hospital. Maybe it's an urban hospital with a certain sort of level of income among the population. And we want to make sure that that model can generalize to a new hospital where, say, is in perhaps a rural area with different levels of income or generally access to care. Now, the challenge there is that shifts in these unobserved variables, particularly in this example, you can imagine will influence not just our features X, but also potentially our outcomes Y. So for instance, if you have less access to preventative care, that might influence your likelihood of developing a certain disease in ways that are not necessarily mediated by other features that we observe. And so in this context, we sort of tackle two problems in this work, and I'll talk about them in this talk. The first is, how do we incorporate domain knowledge of what sort of shifts might be plausible? Because we may not be able to achieve robustness to, say, arbitrary changes in these unobserved factors. And perhaps equally salient, how do we protect against shifts in these factors given that they are unobserved? And so this is a one-sentence summary of that contribution. We're trying to learn, in this case, linear predictors that are robust to these, what I'm calling plausible interventions on unobserved variables. And we'll be using noisy proxies as a way of getting at those unobserved factors. So I'm going to start by talking about the high-level setup, including relations to previous work. There are close connections between what we're doing and anchor regression, which I know some people in the audience are familiar with. And then I'll talk about our contributions at a high level before going through them in more technical depth. So the setup here is going to be one of linear structural causal models. So we are assuming that there exists a linear model over all observed and unobserved variables. You can represent that mathematically as follows here. And I'll talk about the proxy part of the assumption in a moment. So in this case, our causal assumption effectively is that, beyond linearity, is that A, which is the variable we're concerned about interventions upon, is an anchor variable. We're meaning in this setting that it has no causal parents. And you can interpret interventions upon A, if you'd like, as shift interventions on other variables that A affects, or for simplicity in this talk, you can think about sort of hard interventions upon A. Where in this sort of equation, B and M are both matrices, just to clarify that. And X and Y are our features and outcome, and H is other potential hidden variables. And so representing this graphically on the bottom left, I've drawn a little lightning bolt on A to indicate that that's the thing that is changing. And the nice thing about this framework, which is originally put together here in the anchor regression paper, which I'll be talking about a bit more. The nice thing about this framework is that it captures a lot of forms of shift, a lot of potential causal graphs at least, that correspond to different types of shift that people consider in the general machine learning literature. Now, our goal is to do two things. One is we're going to try and use noisy proxies of these anchors, which we're assuming are not observed directly, but are only observed indirectly by these proxies at training time, to construct a model that is minimizing a worst case loss over a set of interventions. And I'll also talk a bit more about that, constraining that set in sort of interesting ways, where this is the sort of objective we're optimizing, we're minimizing a worst case loss under those excuse me, interventions under a mean squared error criterion. And so now I'll talk a bit about background. We're not the first person to consider this sort of objective and model. And I'll start with this sort of simple example. This is just one example, obviously captured within our sort of class of graphs we can consider, but I like it. It is a slightly modified version of an example from the original anchor regression paper because it builds some intuition for trade-offs between robustness and accuracy, and is going to lay the groundwork for walking through our contributions and so on. So in this setting, A is an instrumental variable. If you don't know what that means, don't worry about it. It just means, roughly speaking, that the graph looks like it is here. And you might ask in this setting, well, what predictor should I use if I want to be robust in some sense to interventions on A? And you might start with two candidates, the causal predictor, which in this one-dimensional setting, if you look at the structural equations at the bottom, is just one. Or you could look at the OLS predictor, which is in general not one because of this confounding via H. In this case, it's something like 1.67. And the place where you might start is you might observe that X and Y are both linear functions of A. So I've just written Y here where I've replaced X with the structural assignment of X in the equation for A, or in the equation for Y. And as a result, the residual itself is a linear function of A. And because we're worried about mean squared error, we're really worried about the residual. And here we can see that there is a term that depends on A, this linear term, plus another term that is independent of A, but includes things like gamma and other random variables. And here we can observe that the causal effect, picking gamma equals 1, yields in some sense invariant performance. Our residuals and therefore our mean squared error becomes totally independent from A because 1 minus 1 is 0. Of course, that's not the full story. Here, what I'm plotting on the right-hand side is, and I'll sort of talk through why it's not the full story here. On the right-hand side, on the x-axis, I'm plotting hard interventions on A. And on the y-axis, I'm plotting the mean squared error of a predictor under the distribution that results from those interventions. So the OLS predictor, which whose error I'm plotting here, is a fixed predictor. This is trained on the original training distribution and evaluated on these distributions where A has been intervened upon. And now here, the training distribution of A is mean 0 with unit variance. And you can see that as, for large interventions on A, the performance is quite poor, but if they're close to 0, it's reasonably good. Now this line that I'm now plotting is the line for the causal effect. And this is, you can see invariant to interventions on A, but it is also giving something up. There's a cost there where for interventions on A that are not too large, we can see that the performance is much worse than OLS. And finally, this is anchor regression, which I'll explain a bit more in a moment because it's connected to what we're doing. And the nice interpretation of anchor regression that you should have in your mind is that it is optimizing a worst case loss within a robustness set, as shown in this example by the gray area. So it has the optimal worst case performance within this set. And you can sort of tell that by looking at the endpoints here and seeing that they're doing much better than either OLS or IV. And the trade-off here is between invariance and in-distribution accuracy, which is achieved by choosing a particular objective. And a lot of our contributions will involve different objectives that look similar but accomplish different goals. So there's a least squares loss here, plus a regularization term that penalizes the influence of A on the residuals. And the result is this nice guarantee from the original paper, where this is minimizing a worst case loss. Here I've used R gamma to denote the residual just for simplicity of notation. And if you don't entirely follow the sort of guarantee in the bottom, it's essentially a multidimensional version. I've shown the deterministic case here for simplicity, but there's also a random version of this where the interventions are allowed to be random. If you don't fully grasp sort of what's shown here at the bottom, don't worry too much about it. We'll talk about it in a bit more depth later on. But you can think of this as the multidimensional analog of the one-dimensional picture I just drew. And so with that background out of the way, we'll talk a bit more about our contributions, first at a high level and then going through them in a bit more detail. And this first part that I want to talk about is this robustness to quote unquote plausible interventions. And now you might rightly ask, well, it seems like we've already done that by talking about anchor regression. There is some sense of bounded interventions that seems plausible. And the distinction that I'm going to draw here is, what if we have more specific knowledge of the essentially direction of shift? So for instance, we might know that we are moving from a hospital with a relatively high level of income, maybe in an urban area, to a hospital in a more rural area. Maybe the level of income is different. Maybe the distance to the hospital is different. And we might want to protect against particular types of shift. And that might be represented by this robustness set that I've drawn here, where it's not symmetric around the origin, but is instead kind of pointing in a particular direction, while perhaps still capturing some of the training distribution. And our first contribution is a method for essentially generalizing anchor regression to these types of, what we refer to as more targeted robustness sets. And we creatively call this targeted anchor regression. But if I toggle between these, you can get a sense for what's going on. We're able to get better performance in kind of these arbitrary robustness sets, but we're giving up something outside of those sets. And then the second contribution here is to talk about how to do all of the above with unobserved variables as anchors. And to understand how we solve the problem, it is perhaps useful to understand first what the problem is. So I've plotted here on the right the same thing that I've plotted several times, which shows the error of anchor regression and other approaches when A is observed directly. When A is not observed directly, and instead we run anchor regression just as we normally would, same hyperparameters, but we use a noisy proxy of A, we can see that the robustness set, you can sort of see that the robustness set is reduced. But visually in this figure, if you look at the dark orange line, you can see that anchor regression starts to look a lot more like OLS. And that's going to be something which depends on the level of noise in the proxy. So one of our contributions here is to demonstrate that in a more sort of precise way in the general setting, that noise in a single proxy provably reduces the robustness guarantees of something like anchor regression. But of course, no one likes to introduce a problem without a solution. So we also note that if two proxies are available, we demonstrate how to use two proxies to recover the original guarantees of anchor regression as if A had been observed. And that's something we call cross-proxy anchor regression, which is shown here in purple on the figure, which sort of perfectly overlaps with the anchor regression guarantees. So that is our approach at a high level. Maybe I will pause here briefly in case there are any quick clarifying questions.
Thank you, Michael. We don't have questions at this moment.
Okay, wonderful. So I'll keep going and I'll go through some of these things in a bit more depth. So I'll start with this notion of robustness to targeted interventions. And it'll be helpful here to generalize from the simple one-dimensional example that we talked about, where these robustness sets are in some sense very simple. It's just an interval somewhere on the real line, to robustness sets in multiple dimensions. So I'm going to have some plots that look like something on the right. And the way to understand those is they're just the two-dimensional version of this sort of one-dimensional robustness set that we've been talking about so far. So here, for instance, you might imagine one dimension is distance to closest clinic. Another one is income. We may have many other dimensions of unobserved variables that we're kind of concerned with. And this is how we will visualize them. So to understand the guarantees of anchor regression in this sort of two-dimensional setting, here we've plotted in gray dots, perhaps examples from our training set. And this gray ellipse is the covariance, is meant to represent the covariance of A in our training set. And then what anchor regression is doing is it is optimizing a worst case loss over interventions in a rescaling of that covariance, which is controlled by this parameter lambda that we've seen before. And our approach, targeted anchor regression, allows us to optimize a worst case loss over an arbitrary ellipsoid robustness set in this case. So for instance, here we might know that, future hospitals will either look something like our current hospital, or they will have populations who tend to live closer to the clinic and maybe with lower income, but we're less worried about other directions of shift. And the upshot of that is by constructing more, in some sense, narrow robustness sets, we're able to make a different robustness and accuracy trade-off. So our general formulation is sort of given below in terms of the guarantees, but it's visualized here on the left for a specific example. You can note that in some sense, anchor regression is this generalizes anchor regression in the sense that you can pick parameters mu and sigma such that it recovers the original anchor regression objective and guarantees, where this parameter mu controls the center of this ellipsoid and the parameter sigma controls the shape. To get a bit more concrete here, I'll just talk briefly about what the objective looks like. So in anchor regression, we have the least squares loss plus this regularization term. You can view that regularization term in the following way, where it is encoding with this, what I'm calling B gamma, the causal effect of a shift in A on the residual. And that shows up in this kind of quadratic term. And viewing things this way, you can see a similarity to our proposed objective here. To be clear, we're talking about population quantities throughout. So this is all sort of these expectations are, for instance, the population expectations, where I won't dwell too much on this form due to time, but if you squint your eyes and maybe stare at this page for a bit, you can probably come up with the values of sigma and mu that reproduce the anchor regression objective, but also generalize to other cases. Now I'll talk in a bit more depth about this idea of using noisy proxies. And to do so, I'm going to first have to define a bit better what I mean by a noisy proxy. So in this setting, everything is some linear function with additive noise. And so our proxies will be no different. They're assumed to be linear functions of A with independent additive noise. And you could think of this as, for instance, in the socioeconomic sort of indicator setting, having data like self-reported data from patients on some of their sort of social determinants of health. But you could also imagine having third-party data, which is actually relatively common in sort of healthcare settings. Basically people who have tried to guess, some certain factors about people. And we'll assume that both of these are linear functions of A plus additive noise. And now returning to our one-dimensional case, when A is observed directly in this specific example, anchor regression is minimizing a worst case loss over this particular set. But what happens when we only have one proxy? So before I showed this curve, this dark orange curve on the right-hand side. But now what I've also plotted are these dotted orange vertical lines. And those actually indicate the worst case robustness set that anchor regression is effectively optimizing over when a single proxy is used. So there is still a worst case kind of robustness guarantee, but it is in a much reduced set, or potentially much reduced set. I say potentially because it depends on the signal to variance ratio of the proxy. And this in general is not identifiable from data alone. So we might expect that there is some reduction in robustness, but we're not able to tell just from a single proxy how much our robustness guarantees have been reduced. Intuitively, a lot of noise in a proxy will make it look like the errors are pretty independent from the thing that we care about, but they may not actually be independent from A. That may just be, or they may have low correlation with W because there's a lot of noise in W, even if they have a high correlation with A. With two noisy proxies, we're able to recover the original guarantees, as I mentioned. And the general idea here is in the simple one-dimensional setting is that here beta Z and beta W, the coefficients on A for each of those, have to be non-zero. And that's intuitive. We need both of them to carry some signal about A. In the multidimensional setting, the picture looks similar, though I would just note here that our reduction in robustness set can be different in some dimensions versus others. So for instance, if there's more noise in whatever we're using to try and get at distance to closest clinic, we might have less robustness along that direction and so forth. But as I stated before, we can recover the original robustness set using 2 noisy proxies. And to talk briefly about how we do that, I'll go through the objective in a little bit of detail. So here I'm just comparing a straight anchor regression. There is a variant of this that works for the targeted case as well, but simpler to see in this setting what we're doing. Our objective here, which we're calling cross-proxy anchor regression, involves this term that is a similarly regularization term, but just includes W and Z, because of course A is not observed in our setting. And we can write both of these equivalently as the following, where you can see that they take a similar form, except that we've replaced A, which we don't have, in some cases with W and in some cases with Z, really exploiting the fact that under our assumptions, the shared variation between W and Z is entirely due to A. And this, we show in the paper, is equivalent. These terms are in fact, population equivalent, assuming that beta W and beta Z are full rank. And so that's sort of the generalization of that non-zero assumption in the one-dimensional case. We also extend this, as I said, to targeted anchor regression, allowing for identification of more general worst case losses. But I'm going to switch over to talking about some experiments in the paper. There's plenty of cool synthetic stuff. I'll talk a bit more about our real data experiment. So our goal here is to predict pollution given data from a couple of cities in China, where we have weather-related variables, and we would like to predict pollution level using those variables. And because there's a lot of seasonal variation, we are going to use temperature essentially as an anchor variable in the setup, where to do our evaluation, we'll take 3 seasons worth of data for an individual city. We're going across seasons here, not across cities, and train on those 3 seasons and hope to be robust when we evaluate our predictor on a held out season. Some of the results are given here on the right. The first observation is that when we use OLS, we get a certain average mean squared error. When we use anchor regression, having tuned the hyperparameter using the sort of leave one season out cross-validation, we end up with slightly better performance. And the targeted approach achieves another kind of improvement in performance, though I would caveat that with it being a slightly optimistic version, where we know something about the mean invariance of the temperature in the held out season to kind of construct our robustness set. We also have some other baselines in here, which I won't have as much time to talk about. So I will sort of elide over those, read the paper for more detail. We also have some other statistics here. So out of 9 scenarios where we ended up comparing these methods across like different seasons in different cities, we see that a certain number of times out of 9, anchor regression, for instance, improved upon OLS in 6 out of 9 scenarios, and we have a best and worst case difference as well, where lower is better. And we also compare proxies. Now the challenge here is we want proxies that sort of satisfy our assumptions. So what we do is we take temperature and we add Gaussian noise to generate 1 or 2 proxies. And in the targeted case, we see that with 1 proxy, that's the second row, performance deteriorates a bit. But with 2 proxies, we're able to recover the original kind of targeted performance using our approach. And we see a similar, though a little bit more subtle, you have to look at the best case column, trend with anchor regression. So just to wrap up, we've talked about following contributions in the linear setting. I think the broader goal here is really constructing domain-specific robustness guarantees. So part of that is specifying the relevant factors of variation that you care about. Oftentimes, I think those are unobserved things. So you're going to have to use proxies in some way to get at them. And then second, focusing on more flexible sets of shifts to allow domain experts to really hone in on what sort of shifts we would anticipate happening in the future. Obviously, there are plenty of open questions here. A big one is, everything here was in linear models. So how do you extend it more broadly? Happy to talk about that. Not that I have great answers, but happy to talk about that question in the Q&A if folks are interested. But I will close there because I believe that's about all the time that I've got.
Yeah, thanks for the very nice talk. I have a few quick questions. First of all, so the proxies result that you showed, if you would have a link between the proxies, would that be an issue? Or is it something that is fine?
A link directly between the proxies is an interesting question, but I think you would have an issue. I mean, the main, the intuition here is that if you look at I'm pretty sure you would have an issue. If you look at the correlation between the two proxies, that's essentially telling you how much of the variation in a proxy is due to A, because you've assumed that the only way that they can be related to each other is through their shared variation.
Would you still get some sort of minimax guarantees in your intuition, or would you kind of get a protection exactly the wrong direction?
I mean, I think you would, if only because you still get a minimax guarantee when you only have one proxy. Okay. And the intuition here a little bit is actually there's a connection to measurement error literature. I mean, no surprise, and regression dilution. So effectively, what you're doing with anchor regression is you are able to predict the residual as a function of A. And you can think if you have noise in your copy of A, then that's going to change the regression coefficient in some way. And so it'll come down to sort of how much are you able to correct for that? And you sort of can with two independent proxies. But anyway, yeah, that's a related piece of intuition.
Great, thanks. Maybe could you just very quickly comment on extending to nonlinear models? I've also thought about this, and I know it's a tough problem, but if you had any thoughts, that would be great.
Related to what I just said, I think a big question is what you want to keep and what you're okay with losing. I think, part of what enables all of these results is the fact that, as I said before, you can kind of predict the residual as a function of A, kind of for arbitrary values of A because it's a linear function. And so I think, part of this is designing what you mean by nonlinear anchor regression. And I really like the kind of intuition and interpretability of shift interventions. And you might think, can I still keep that sort of nice, simple description of interventions, but in a more restricted class where I really am looking at bounded things that don't force me to extrapolate too far away? Be my very quick answer, but.
Great, thanks. Yeah, I think we currently don't have questions in Q&A, so maybe wrap up.
All right.
Jingguan, do you want to wrap up or should I? I'm here. Jingguan, I can't hear you.
Okay, sorry, I'm having some trouble with my Zoom, so I can't share that final slide. But I'd like to thank our speakers again for their great presentations today. I can see a lot of interest in the Q&A, and so for the interest of time, let's close today's session. Next time we will have Zijian Guo from Rutgers University, who will tell us some of his latest work, and in the discussion we will have Frank Windmeyer from Oxford University. I hope I'll see you next week.
Thank you.